This is lecture number 12. Let's begin with the summary of the previous lectures. In the previous lecture, we started to discuss about the quantum circuit. And then I gave you an first example of the quantum swap gate. And then I also pointed out that compared to the classical counterpart, the quantum circuit generally does not allow the loop. And there is no concept of the fan out similar to the digital circuit. And also I generalized the concept of the control NOT gate to the controlled U gate. And finally, I also gave you the explain the measurement symbol, which is typically used in the description of the quantum circuit. Um, and another important, yeah, probably one of the most important theorem in the quantum information is that is the no cloning theorem. And then what it says is um, it does not say that you cannot have the identical quantum state for many of the qubit. What it says is if you are given some arbitrary quantum state by someone, and then or yeah, it is generated from somewhere else, but you don't know the history of that quantum state, meaning that how that quantum state is created or what is the current quantum state. In that case, you cannot reproduce the same quantum state when you are just given a single pair. Yeah, so that's what the no cloning theorem says. And and also I discuss various perspective of the measurement in other bases. What when we are only discussing about the measurement in the zero and one basis, we call it as a computational basis. But in quantum mechanics, there are a lot of you need to measure the given quantum state in various bases. And then, so that's why we need to understand the measurement in other bases. And then, in principle, if you have to measure some quantum state in other bases, but if it is easier to measure in the computational basis, what you can do is apply the basis transformation or unitary transformation before the measurement. And then the tip um, for the polarization case, sometimes it is not necessary to do the first unitary transformation, and then you can just rotate the polarizer to measure the polarization. But that's only when that is possible only for some limited case. And in many of the case, it's not easy to just change the measurement device. So in that case, and especially not only for the polarization, but if you have to measure the um, quantum state of the two-level atom or some other atom, then generally you cannot measure those quantum state or qubit information by using different bases. So the practical way to implement the measurement in other bases is to rotate the basis before the measurement. And then I also introduced the Bell basis, which is the complete basis in the for the 2-qubit space. And then I also showed you how to generate a Bell basis from the computational basis. And then you can also reverse that process, and there will correspond to the basis transformation necessary for measurement in Bell basis. So today we are going to continue the discussion about the quantum entanglement, and then yeah, the main and one of the motivation is that you probably saw some of the news talking about the Chinese quantum satellite succeeded in distributing the quantum entangled state. It was 4 years ago, where it was 2017, and then yeah, it was a very big news for not only for China, but it was important news over the world. And then, but yeah, many people don't know about that, the meaning of that experiment. So yeah, I want to explain this one in more detail because it is directly related to what we cover. And another reason I'm also interested in introducing this one was uh, they used two, yeah, what they did was they created a quantum entangled state between two photons. So it is basically they were generating the entangled photon pairs, and then they created the two photon, and then those I will call this photon as A and this photon as a B. Yeah, so these are the photon qubit, and then their quantum state is can be expressed in this way, and then the yeah, and then I also want to emphasize that the entanglement generate entangled photon source they used in their satellite is what I actually developed while I was a graduate student. Yeah, so it was actually a long time ago, yeah, more than 10 years ago, and then they eventually adopted my scheme, and then they basically reproduce what I demonstrated more than 10 years ago. Yeah, so yeah, so let me yeah, to explain how to generate the entangled photon source using the photon, then it will take a while. So yeah, um, um, I will introduce how it can be done when I have time at the end of the semester. But I cannot guarantee it, yeah, because the topic is a little bit off from this course. But yeah, let me just explain the physical meaning of that experiment. So if you look at this quantum state, and then let's say first case, we are assume that so this satellite generate two photon, and then each of the photon was sent to the ground state, and then these two states were separated by more than 1,000 kilometers or something like that, and then this station received the photon, and then they wanted to measure the polarization state of these two photons, and then let's first assume that these two stations wanted to measure the quantum state of these two photons in HV basis, horizontal vertical basis. And then what happens? Well, yeah, we know that they wanted to measure the this photon in the HV basis, and then this is the quantum state of corresponding to these two photons. So yeah, if you remember the third postulate in the quantum mechanics, what happens is if we have superposition of multiple bases or multiple state, multiple term, and then the measurement will only happen for one of them. Yeah, so let's assume that the quantum state collapsed to this quantum this part. That means that the station A will measure horizontal polarization, while the station B will measure vertical polarization. But that's not the only option. Well, yeah, because if you calculate the probability of measuring this one versus this one, then the probability amplitude of this one is 1 over square root of 2. And then to find out the probability, then we have to square them, which is 1 over 2 or 0.5. So we know that either this state or this state has the same probability of 0.5. So yeah, if we try 100 times, then on average, 50 times of the measurement, we will obtain this result. But for the rest of the 50 times, we would obtain this result, which means that A station will measure the vertical polarization, while the B station measure the horizontal polarization. So that's the property of this one. But the more important is or and then and what this means is that their measurement will be the measurement at station A and station B will be always opposite to each other, and then we sometimes call it as an anti-correlation. The more interesting case is what happens if station A and B try to measure the measure the polarization not along the HV basis but in the DA basis, diagonal and diagonal basis. Well, let's consider a little bit carefully. Let's assume that um, if the state is this one, HV basis, HV state, then we know that the station A will receive polarization H, but we are trying to measure it using the DA basis. And what is the probability of measuring D when the input polarization is H? 50%. And then what about the A? Yeah, 50%. What about the station B? When this when we consider only this term, then we know that when station A receives H, then the station B will receive V, and then if we measure between the D and A basis, we know that the V can be decomposed into D and A with the equal probability amplitude. So again, this one can be appear as either D or A. You have half and half. What about the other opposite case? If H goes to here and vertical goes to here and horizontal goes to here, still the probability is the same, D over A and D over A. And moreover, for example, if we have H and V like this first case, assume that station A received D. What is the probability of measuring D in station B? For this case, for this H and V case, when the station A measured the D, what is the probability that station B will measure D? Well, if you are naive, then you would say that these two are the decision whether D or A will be measured for this photon is independent of the decision for the measurement of V in DA basis. So there is 50% of chance measuring D and then the same amount, 50% of chance of measuring A when the V came to here. So the decision between these two for station A should be completely independent of the decision between D and A in station B. For when we have this H and V, then what about the opposite case? If we have V and V have H here, is there any difference? Probably not. So you might say that, first of all, there are all 4 possible cases, meaning that station A might measure either D or A, and then station B might measure D or A, and then when station A measures D or A is independent of what station B will measure between D and A. But that's not the case when the entire quantum state is like this, or entangled state. So the answer is their measurement, DNA and DNA, will be anti-correlated again, like HV cases. So that's the most surprising fact with the quantum entangled state. And then you might still be convinced. So let me show you in mathematics or in more detail. So we are interested in the case 2. So let's focus on the answer to the case 2. What happens if station A and B try to measure respective photon in DNA? Well, to decide what will happen in the measurement in DNA basis, we should rewrite the previous entangled state, which was psi minus, in terms of DNA basis. How can we do that? Well, yeah, we know this relation, so we also know that the D and A bases can be represented as the superposition of these two states, which we already dealt several times. And based on this one, we can also reverse the relation, meaning that we want to express H and V basis in terms of dA basis. That's easy. You can just add these two lines together. Then you will obtain H. While if you subtract the second line from the first line, then you will obtain V basis in terms of the dA. So these are the results. Then what can we do? Well, let's go back to the original psi minus expression. Then I want to express this state in terms of dA basis. Then all I have to do is replace H with dA and replace V with dA again. So that's exactly what I did. Yeah, so this H is replaced by T plus A, yeah, coming from here. And then but these are still, both of them get A index, while the second photon, which went to the B station, then it will have the B index. But we know that V can be decomposed into the T minus A. Yeah, so I replace here. And I should still have this minus sign here. And then finally, the second term has the V for A station, and then H for the B station. So yeah, the overall expression looks like this one. Now what I can do is expand this product of two product of the sums. Then the first term will be expanded as the summation of the full term, which is D and D term and D and my A, but there is a minus sign, so it is minus D sub A, yeah, and then A sub B, and now yeah I can distribute this one, which is A sub A, T sub B, but with the plus sign for both cases, and then finally the last term, which is plus minus, so overall minus, and then A sub A and A sub B, which is here. So this first line is this term. And then if you just follow the same rule, then the second line corresponds to the expansion of this one. But you can note that this term and this term are very similar to each other, except that there is some difference in the signs. So if you just carefully expand these two terms, then yeah, they will be just expanded. This second term will be expanded in this way. Now we can do some math. Well, this term and this term looks exactly the same, except that it does not, it has the positive sign in front of it, or a positive face, and this one has negative face. And then yeah, they are just algebra, so they will just cancel each other. What about this term? This is minus and this is plus, but we have to multiply minus, so it is actually 2 times. And yeah, so there was actually 2, and then here it is plus, and then there was also 2. And final term, yeah, it is minus, but minus will plus, so they will cancel. So there is nothing. And then the reason I don't have the 2 in front of here is that because yeah, originally we used to have 2 square root of 2 in the denominator, and then they just cancel with each other. So yeah, that's why it is looking like this one. So what does this result mean? Well, if you remember that when we interpreted this term, we said that the third postulate of the quantum mechanics says that it will either collapse one of these two terms, and then only our measurement will be either H and V measurement in each of the station, or V and H measurement in the each of the station, but there is no such kind of thing like a HH case or VV case. So this was called as anti-correlation. What about the measurement in the TA basis? There is no DD or AA case because they just canceled with each other. And then what this means is that when we measure this original state in the TA basis, we would either A station measure D and B station measure A state anti-diagonal polarization, or A station will measure um, anti-diagonal polarization, while station B will measure diagonal basis. However, there is no combination like DD or AA. So it was completely opposite of our intuition. And then, yeah, in this case, it was still anti-correlation. So that's why I could claim that, yeah, they will be always appear like this one. And then for this case, in principle, if you go back to this original calculation, there was actually possibility that this DD will happen because these terms were there. And then what happened? They just cancel each other. And we call this one as call this kind of situation as a destructive interference, while we call this case when they survived, they were constructively interfered. And why do I call it that way? Because, yeah, you can see that, yeah, these two terms cancel it with each other, and then yeah, that's why we care about the phase. If we didn't care about the phase and it is only the probability, then they would just add with each other. However, when we are dealing with the quantum state, we have to be careful about the phase, and in this case, they are opposite phase, and that's why they cancel each other. And then that's exactly the same when you have two sinusoid, and then if they are in the same phase, meaning that when they are the max, one of them is max, the other is max, then if you add them together, then their amplitude um, will be increased more than their sum sometimes. Well, in this case, they might just look at those simple summation, but yeah, I will show you what I mean by that. And then what's more interesting is that if we have opposite phase like this, then if we add these two wave, then even though there was some waves in both cases, if you just add them together, then they will just become zero, or it does not oscillate at all. And so this is exactly what happened to TD case or AA case. So they just cancel with each other. And I said that these were destructive interference, while I call this one as a constructive interference. And then the property of the constructive interference it is more probability than if you just calculated individual probability. For example, if we have this term and this term separately, or consider individually, then what is the for the first case, what is the probability of measuring TA for the first case? In that case, what we have to do is find out the probability amplitude in front of here, but it is not the only minus, but we have to also consider the denominator. So it is 1 over 2 square root of 2. And then, yeah, to find out the probability, we have to square it, which means that it will be 1 over 8. And then what about the other case? So for the second line, then we still have the same option. And then in this case, it is plus, and then but they have the same value. So if we square them, then it will be 1 over 8. So the overall probability looks like 1 over 4. However, after the constructive interference, what is the probability of dA? Well, minus 1 over square root of 2. So if we square it, it is not 1 over 4, it is 1 over 2. So if we individually counted each of the term, the summation of the total probability is only 1 over 4, while if we, after the constructive interference, if we calculated the probability, it is actually increased compared to that one. So that's why it is called as constructive interference. And then, yeah, the most important intuition you need to have when you are dealing with the quantum mechanics or the quantum circuit, then you should try to increase the constructive interference for your solution, and then you should try to kill or destruct all those unnecessary terms by destructive interference. Yeah, well, yeah, for here, yeah, you probably cannot see why it is related to the algorithm or quantum algorithm, but you will see it when we consider the quantum algorithm in later lectures. And moreover, yeah, this anti-correlation relation is not only limited to this AD basis. As a homework, you will be required to prove that even if as long yeah, so TA is the special case that the theta is the 45 degree, but this kind of anti-correlation relation is valid for any arbitrary theta. So that as long as these two bases are orthogonal to each other, but not necessarily they form a 45 degree, then the resulting state will be anti-correlated like this one. So the next question is, well, yeah, the previous example was a little bit weird, but then can we reproduce the similar result or same result using the classical device? Or let's say that there is some conman who wanted to get some money from you, and then that conman somehow tried to make a fake device which behaves like entangled photon source. Yeah, for example, yeah, Chinese scientists wanted to buy the um, entangled photon generator for their satellite. And then how can they confirm that it is a real quantum entangled photon generator rather than some classical device or some fake device? Well, yeah, let's try to simulate what we need. For the case one, we wanted to measure the polarization state in the HV basis. In that case, we know that when we have some generator, which will, so this is quantum information, quantum entanglement generation device, and then we want to have when this photon has the H polarization, we want to have this V polarization, and then if this one emit the V polarization, and this will emit the horizontally polarized light. Then if you only measure them in HV basis, you can actually make this kind of device using only the classical technology. For example, if you have some kind of random number generator, or more likely you have some um, coin flipping device, and then if you just flip the coin and then just receive and then check whether that that coin is head or tail, and depending on whether it is head, if it is head, then we would say that, well, yeah, then let's send the horizontal polarization to the A, and then vertical polarization to B. And then if the coin shows that a tail, then let's send the V to here and then horizontal to here. So yeah, if you only measure uh, polarization in the HV basis, then it corresponds to case one, and then there is no difference whether you have a real entangled state or a superposed state, or this coin flipping device, coin flipping classical device. So how can you confirm that it is the real entangled source, not the fake device? That's by if you if you measure the polarization not only along the HV basis but use the DA basis. But what you should be careful is that you should never tell you should never tell whether you will use HV basis or TA basis for each of the measurement. So maybe you and station A and station B might agree that they will randomly choose H and V basis, but they might just agree that when they will use the HV basis and then when they will use the TA basis, and then the generator actually cannot know whether they will just use the HV basis or TA basis for the next trial. So yeah, what the generator can do is just use only the HV basis, and then um, if they are unlucky, and then when they and A and B use the TA basis, yeah, diagonal entire diagonal basis, then sometimes the for the fake device they will measure some inconsistent result, meaning that not always the anti-correlated, but sometimes it is the same diagonal or anti-diagonal will be measured, and based on that measurement, then the tester can say that well, your device is fake, so yeah, I won't buy your device or something like that. So you can in principle distinguish the fake device and the real quantum entanglement device. So yeah, so yeah, there are a lot of interesting parts related to quantum entangled state. So that is the most perplex situation, and that's why it was called as the EPR pair or Bell basis. And then there is a lot of confusion when you hear what I just showed you. So if you remember that with the quantum entangled state, the measurement between two locations, they will be always anti-correlated. Then many people try to interpret that as that the communication is even faster than speed of light. And actually, yeah, if anybody asked me whether you can implement the communication faster than speed of light by using the Bell basis, the answer is definitely no. And then yeah, there was very interesting news article in the past. Yeah, this was the news article right after that Chinese satellite experiment succeeded. Then the news reporter somehow interviewed some of the experts in Korea, and then then um, uh, uh, this expert said that it is not possible to do any communication faster than speed of light, even using the EPR pair. But the reporter just write that um, whatever he wanted to believe. Yeah, so yeah, there was initially yeah, this kind of um, um, statement that it is possible to do the communication faster than speed of light. And then that expert later checked that news article and said that in the reply that I'm the person who interviewed. And then I said that it is not possible to do any communication faster than light, but the news reporter just misunderstood his comment, and then made a mistake in the news. So eventually it was fixed, but it is common misunderstanding that people believe that the what I showed you in the previous case, that if you make the measurement in the if whenever you make a measurement using this kind of experiment using satellite, then people had the tendency to believe that they can do the communication faster than light. And the reason, even though it looks like the when the station A measures the H, even without asking station B, station A knows, or let's say person A and person B say that even if person A measures its own um, polarization, then it can know immediately what does person B will measure. So it might sound like it is a immediate communication. Then why it is not the communication? Well, and then this similar situation was also confusing Einstein, because then Einstein was the expert in the light, and then he also knew that nothing can move faster than the speed of light. So how can the information can be delivered is transmitted faster than speed of light? And the answer is, in this measurement, there was no transmission of intention. If you think about carefully, what is the purpose of the communication? It is the transmission of my intention to somewhere else. And then here, we know that station A and station B will definitely know what the other station measured as soon as it measured its own value. But does that mean that station A transmitted any of its own intention to B? Yes, all the communication can be done either by sending 0 or 1 value at each of the time, or each of the time frame. So we know that A and B will always measure opposite value, like a 0 and 1 or 1 and 0. But does that mean that station A transmitted any of the information? Actually, no. Because if you can decide whether you will measure 0 or 1 at the next time, or in the next measurement, then there will so if station A can decide that next time it will measure 0, then we know that B will measure 1, and then station B will immediately know that A wanted to measure 0. However, the measurement, which one will be measured, is not cannot be controlled. It is completely random, and then that is the property of the quantum mechanics. So we know that there is a very strong correlation in those measured information, but just having the information doesn't allow you to transmit any of the information. I know it is very confusing, but if you really carefully think about what happens, then there is no real information transmission. And then that's why it took so many years until people figure out that it is not violating the speed of light limit. And at the time when Einstein was active, he was not clear about the concept of the information. So he could not think such kind of interpretation until he dies. But that's why it is necessary to combine the concept of the information and the concept of the physics together. And then that's probably one of the triumph of the quantum information. Another frequently referred situation is the Schrodinger's cat. And then many of you heard about the Schrodinger's cat. And then let's if I summarize the meaning of the Schrodinger's cat, it is this situation. It is something called as Gedanken experiment, or in other words, it is imaginary experiment. Yeah, so Schrödinger somehow assumes that what happens if this kind of situation happens. So yeah, the situation is the following: the cat is enclosed in some kind of box, and inside that box there is radioactive material, something like uranium or some other things. And then uranium can actually decay, and then that decay, the time when it will decay cannot be controlled. And then that randomness is actually explained by the quantum mechanics. So when it will decay is actually we cannot predict when it will decay, because it is a superposition of the decay many different decay time. Yeah, so whether it will decay at time equals 0 or time equal 1 or time equal 2, they are all superposed. So that's why it is unpredictable. And then so in such kind of superposition case, we say that when the when this decays, then this decayed the material will actually trigger one of the apparatus, and then this apparatus will actually break some bottle containing the poison. And then when this bottle is broken by this apparatus, then the cat will die. The question is, because after some period of time, we don't know until we measure the the quantum state of this one. It is in the superposition state. So until we open the box, we don't know whether this cat has died or still survived. So that means that the atomic state and the Schrödinger cat are actually in this kind of entangled state. And then the question is whether the alive and the dead state can be superposed for some animal or even for person. And then in real life it will be very unlikely, because that if for this cat to remain in the superposition state, then nothing should measure this uh, um, cat. But because a cat cannot live in a vacuum, so it will have a lot of interaction with its environment. So before it will remain as the superposition state, it's live, whether it alive or the dead will be immediately measured by some of the surrounding material. So that's why it is not that's why usually we cannot measure the superposition state of the this macroscopic animal. However, people actually produce this kind of superposition state using some of the classical state, classical looking like state. Yeah, so it's not easy to explain why that kind of state is considered as classical, but it was very similar to the laser, and the laser is generally considered as the classical state, where the output of the laser is considered as a classical state. But still, we can have some kind of superposition of different types of laser output state. And then that was somehow considered as the equivalent to the cat state. So yeah, if you look at the some of the research article, then you can see that yeah, people generated Schrodinger cat state or Schrodinger kitten state. Yeah, sometimes. Also, yeah, another similar situation is the what the Einstein says that Einstein said that um, when if the quantum state of the quantum state is only determined by the measurement, and then before the measurement, if the if any system can be in the superposition state, then is that possible that the moon is also in superposition until no, somebody really looks? Or can we be ever sure that the moon is there when nobody looks? And so it is an extreme analogy like Schrodinger's cat. And then that's why Einstein did not believe in the um, superposition or the quantum mechanics. But that's yeah, and then yeah, again, yeah, his such kind of attitude actually helped the development of the quantum mechanics a lot. Related to the integral state, the most important application is the something called as a quantum teleportation. I assume that you are familiar with the concept of teleportation. Well, it is not real, and then in the SF movie, or yeah, I don't know whether you know about the Star Trek. Yeah, that was the one of the popular TV series in the past. And then in the Star Trek or in a similar movie, you see that there people wanted to move some kind of some people from one location to another location without actually traveling. So that such kind of thing was called as a teleportation. And quantum teleportation is a little bit different from that concept because in with the quantum teleportation, we cannot move the material by itself. But the concept is the atom. Yeah, for example, if we encoded the quantum state in one of the qubit here, then it is not like this qubit will disappear here and then the new qubit will just appear here. It is not the quantum teleportation. What quantum teleportation is that the material will still remain here, and then this material is already prepared in the remote site. What the quantum teleportation does is that there will be some quantum information stored in this qubit or the qubit information. Then this qubit information will disappear here, and then it will appear in this new qubit in the remote qubit. Such kind of phenomena is called as a quantum teleportation. So what do we really want to do? For example, well, if we already know about the quantum qubit information stored in this quantum memory, then we can just say that how this qubit information was prepared using the digital communication and then just send it. But here, what we assume is that this quantum information is not well known, or it is, even though it might be prepared, it went through so many steps, so it is difficult to transmit the whole information to here. So yeah, let's assume that this qubit is some kind of arbitrary quantum state. Yeah, and the arbitrary qubit information can be expressed in this way. And to deliver the quantum information from here to here, we need to use the entangled states. So yeah, be careful about the labels. Here I'm representing the entanglement between two qubits, and each of the qubit is labeled with A and B. And this A, and then the information I wanted to deliver or transmit is stored in the qubit labeled with C. So this is here is the information I wanted to deliver. Then what happened? Then how can we analyze this situation? We know that our information is stored in the qubit C, but we also know that the entangled state is stored between A and B qubit. So it is kind of another extension of the tensor product. So the quantum state should be represented in this way. So yeah, psi here represent the quantum state of the qubit C, and then they are tensor producted with um, the tensor product space vector represented by A and B qubit. And then in this case, we are specifically considering the psi minus state. And then we know that psi minus state is expressed in this way, while we assume that our intended qubit to teleport is represented in this way. Now, the protocol to transmit the information stored here to here is following. The first thing we need to do is we need to measure these two qubits, not in the computational basis, but in the Bell basis. So how can we implement the measurement in the Bell basis? Well, yeah, if I expand this tensor product state using yeah, um, using the distributive law, then it will be alpha 0 sub C, 0 sub A, 1 sub B, something like this. And then this one will also multiply to here with this, and then this one and this one each corresponds to here. And then as I said, we wanted to measure C and A vectors in the not the computational basis but in the bare basis. So how can we predict what will happen if we measure the given quantum state in some different basis? Then we have to re-express this quantum state in terms of those bases. And how can we do that? Well, if you recall how we did for the measurement in the diagonal anti-diagonal basis measurement, when we were given the integral state in the previous page, we should first start with the definition of each of the pair bases, which I already introduced before in the last lecture, and then I can rewrite or rearrange this state by adding the first two lines or subtracting the first line from the subtracting the second line from the first line. Then we know that when we add these first two lines together, then only this term will survive and these will cancel with each other because of the different sign. And then we obtain that 0, 1 is expressed as the summation of psi plus and the psi minus. Similarly, we can also obtain the expression for 0, 1, 0 state. And if we also apply those tricks, then we can also obtain 0, 0 and 1, 1 in terms of phi plus and minus. Now, because we have this expression, we can replace this with this expression and 0, 1 with this expression and so forth. So let's say that I already did 0, 0 with this one, which is phi plus phi minus. So phi plus phi minus. And similarly for the 0, 1 minus alpha, and the 0, 1 will be replaced by psi plus and psi plus psi minus, like this one. And if I just keep doing that, this is the next result. And then finally, what I'm going to do is rearrange the entire expression by collecting the common factor of psi plus, for example. Yeah, so if I collect the term which contains the psi plus and psi plus here, and then psi plus, the first term here, the psi plus term has the minus alpha multiplied to the 0b. So that one appears here, minus alpha 0b. And then for this term, it has the beta and 1b. So they will be combined, and then that beta 1b appears here. So that's psi plus state. Yeah, and then what about the psi minus? Psi minus appears here. Psi minus with the minus alpha multiplied to 0. Again, it appears here, and then the psi minus again, and now beta minus 1b. So we should have minus in front of here, but we also had the minus here, and then minus beta. So they all they were all factored in front of this. And similarly, if you just do the repeat the same kind of thing, then you will actually obtain this kind of expression. So what does this expression mean? Well, let's yeah, this is the I just copied from the previous page. So what does this mean? Well, I said that I wanted to measure CA qubit in the bare basis, and now I expressed all the CA qubit in terms of the bare basis, and then they are expressed as the they are represented as the summation of different term with different bare basis vectors. So if I just do the bare basis measurement for C and A, then only one of these four terms will the well, yeah, only one of these four will be measured, and then right after the measurement, if I measure the psi plus for the CA qubit, then I will be left with only this term. Yes, or yeah, if I measure the psi minus for the CA qubit, then I will be left with this one. And what is this? This is exactly the same shape as the original arbitrary quantum state. So what happens is if I can just measure this state, then I can recover the original quantum state. Well, then the problem is it is not guaranteed that we can only measure this one. As I mentioned before, we have no control in choosing which term will be measured when. Well, so what happens if I just measure psi plus like this one? Then I will be left with this term. And is there a problem? Yeah, it is. It is different from this one. However, we know that this state is different from this state only as the factor of the factor of 0, or if I just collect the if I factor out this minus in front of here, then is this part will become minus. So I need to change this phase from minus to plus. How can I do that? Well, we know about the Z gate, which will change, which is represented in terms of the matrix like this way. That means that if we apply the Z gate to the to this quantum state, then this negative phase will be corrected. Then what about the phi minus? If I measure the phi minus, then if you compare this state with this one, they look almost the same except that 0 and 1 are reversed. How can I fix that? Well, if we apply X gate, then if we apply the X gate on the B qubit, then it'll be fixed. So depending on what kind of bare basis we measured, sometimes we don't have to do anything for this case. However, For this case, we have to apply the Z gate. For this case, I have to apply X gate. And for this case, you will realize that we have to apply Y gate. So yeah, depending on what we measure, we have to do some correction. So yeah, and then unless we actually do that extra step, then we don't know. Even though this state might look like this one, but if you just measure this state, then it is actually a completely different state because their alpha and beta is swapped. Moreover, if this state was obtained, then this one still is completely different from this one. So until we um, correct the final B qubit based on the digital information, because I'm calling this one as a digital information because this one, these four states, once they are determined, then that information exists in the digital information. Not it is no longer the quantum information because we measured, and then that means that the quantum state is collapsed. So yeah, we by just sending the digital information, we can recover the original state. Then how can we measure qubit C and A in Bell basis? Well, that is what we learned in the last lecture. I mentioned that by applying the unentangling gate between these two qubits, then and right after applying the unentangling gate and measure the final qubit in the computational basis, then that is equivalent to measuring this original state in the pair basis like this one. So and then yeah, some people also ask that whether this one violate the no cloning theorem, because it looks like we originally had this state and the final state has the same state like original. So do we have the copy of the original state? Actually, no, because I said that we will do the Bell measurement, and then the final result of Bell measurement is definite quantum state or definite digital information. Yeah, so yeah, after the unentangling gate, we eventually measure in the computational basis. So right before the measurement in the computational basis, they might be in some kind of superposition state or some entangled state. But right after we measured the state information or qubit information in the C and qubit memory or quantum memory, they are determined or they are fixed. So there is no point in claiming that they are quantum information. They are now became the digital information or um, definite information, and there is no trace or no relation to the original arbitrary quantum state. So the original information stored in the C now is stored in the B qubit. So there is no copy of the original state, and now this became original. Yeah, so there was no cloning. Yeah, again. And then if you look at this situation, once we measure these two qubits in the pair basis, it looks like the original quantum state is immediately appears in the B state, especially for psi minus. However, from the perspective of the people at the B, they actually don't know whether this first term was measured, or second term measured, or the first term was measured. And depending on which term was measured in terms of the pair basis, until the person at the B side does the proper operation like applying the Z gate or the X gate for this one, the information here is not determined at all, or it is not fixed at all. So yeah, we cannot claim that this one is related to the communication faster than the speed of light, because until we send out the digital information, and then digital information will be delivered slower than speed of the light. So or at the fastest speed, yeah, it will be speed of light. So there is no way you can reproduce the original state over here faster than the speed of light. So up to now, yeah, we discussed about the property of the integral state. So now let's consider more likely the reverse gate property. And then I mentioned that all the gate in the quantum logic should be reversible. So and then if you just think about the classical AND gate or typical AND gate, then they are not reversible. I already emphasized several times. So and the reason is we cannot generally tell what the input was when the if the only the output is given. Yeah, so that's why it is not reversible. But all the operation used in the quantum mechanics should be unitary, and the unitary should be reversible. And then you are familiar with the concept that the unitary operation generally works as a transformation, and then that transformation preserves the orthogonality of the vector in the original space. And then we also know that the unitary operator maps a different input vector to a different output vector. So there is no way unitary operator will map the different vector to a same resulting vector. Yeah, so yeah, that's why it is reversible. Then the question is, can we simulate the quantum classical logic gate or logic circuit using a quantum circuit or a quantum gate? The answer is there is actually corresponding reversible gate for each of the classical logic gate. So it is possible to replace all the digital gate with a reversible gate. However, for the typical classical algorithm, I would not recommend replacing all those typical gate with the reversible gate, because implementing the quantum gate is extremely expensive compared to the digital gate. So there is no way we try to replace all those digital gate with the reversible gate. And also there is a lot of error with the quantum gate. So why do we bother with the um, quantum gate if we can do it can we can if we can solve all the problem efficiently with the digital computer. Yeah, the only case when the quantum computer will be helpful is when the classical computer cannot calculate or cannot do the thing do the job efficiently. Then there is sometimes there is some known algorithm, quantum algorithm, which can solve those problems efficiently. So only for a limited situation, the quantum computer will show the power, its own power. And so yeah, there is some people ask me when the quantum computer will replace all the existing digital computer, and my answer is there is no way such kind of situation will happen, because quantum computer has its own advantage, but it is not efficient for all the applications. So the quantum computer should be used for the specific application, and then for the most of the rest of the job, probably the digital computer will be still efficient. And then now we should to understand how we can replace the digital gate with the reversible gate, I should introduce some of the reversible gate. There are several different types of reversible gate. And then for today's lecture, I will just briefly introduce something called as a Toffoli gate. Toffoli gate looks similar to the CNAC gate, but it is different from the CNAC gate because it has two control. So, and then this somehow behaves, or this somehow implements all the digital logic we can think of, because you know that the in the digital logic, there is a concept called as a universal gate. And universal gate means that any arbitrary digital logic or digital circuit can be always decomposed into the basic universal gates. And then the universal set of the gate is either NOT gate and then the AND gate or OR gate. Yeah, so if you have not an AND gate, then yeah, you can build any arbitrary circuit. Moreover, if you want to reduce the number of the universal gate even further, then it is also well known that the NAND gate or NOR gate by itself is universal or enough. And then um, just in case you are not familiar with the concept, then the NAND gate is looking like this one. And then with this one, yeah, even though it has a two input gate, but if you want to implement the NOT gate, then all you have to do is just to combine um, two input together. Then it behaves like a NOT gate. And then if you want to implement the AND gate, then all you have to do is just to apply that one in front of this AND gate. Then because then it is um, and not and another not. So not and not will just cancel with each other, and then the overall behavior will the overall effect is the AND gate. And how can we implement the OR gate? Well, yeah, there is a well-known property called as De Morgan law, and then that means that um, these two gates are equivalent. So to implement the not OR gate, all we have to do is add two more NOT gate in front at the input side, and then we know that each of the NOT gate can be implemented by this one. So only with using the NAND gate, we can always implement AND or not the component of the universal gate. So eventually, we know that the NAND gate by itself is sufficient, even though it might not be efficient. So to prove that we can implement the we can implement the universal digital logic, or we can implement any arbitrary digital logic using the reversible gate. All we have to prove is that the Toffoli gate, which is reversible gate, can implement the NAND gate. And then it is just in case if you are not convinced, then um, this kind of configuration, which means that the output of the third the target qubit will be reversed only when both of the A, B are 1. And then yeah, so yeah, if you see the truth table, there is no change to C until both of the A and B are the same, are 1. And then for the rest of them, they are the same C appears at the output, and only when the both of the A and B are 1, then the C values are reversed. So that's the kind of controlled NOT gate. And if you express, if you represent this kind of gate in terms of the matrix, then a matrix looks like this one, and then you can confirm that this is the unitary gate. And then yeah, so that's why I can claim that the Toffoli gate is reversible. And then if you consider this kind of input, then this one represent the NAND gate, because we know that the the output of this gate will be reversed only when A and B are both 1. And then in that case, we know that the input will be reversed. And then this one somehow represent that if we add if we provide 1 to the target, then the result is expressed as XOR. And then XOR with 1 means that because XOR uh, we know that yeah, this AB can be either these are just a binary digit or the 0 or 1, and then in that case the XOR with the another one means that always this value will be always reversed, and then we know that this value is only valid when the both of them are 1, so it is equivalent to AND, and then by combining with the XOR, this corresponds to negation. So this overall result is NAND gate. Another, yeah, so uh, because now yeah, we prove that the NAND gate can be implemented by using the reversible gate. So and then we can it is equivalent to proving that any arbitrary digital logic can be still replaced, still implemented by the combination of the reversible gate. There is also, yes, this is the example from the book. And then this, even though, yeah, even the book says it is fan out, this is not the ideal fan out, which I explained before, because this is very similar to the situation with the CNAT gate. So we know that CNAT gate cannot be a perfect fan out, but sometimes this kind of limited fan out still helps. So yeah, I will just mention that this is called as fan out in quantum logic, but also note that this is not the perfect time for perfect fan out you would expect with the digital logic, or this has nothing to do with the cloning. Yes, because this is the function of this one is exactly the same like the CNAT gate. And yeah, before I go more detail, let me discuss about the quantum parallelism. Yeah, so this is very simple example, but yeah, this will give you some insight about the quantum parallelism. So yeah, let's assume that we are given some kind of simple function. Yeah, here, yeah, yeah, this function will just take the one bit information, and then the output will be also one input, one bit information. But then so yeah, you might just think that this will just produce the f of x, but in principle we can also implement the digital logic in this way that the y value uh, well yeah, so for the typical digital circuit, you don't really need these extra lines, but because we wanted to convert any arbitrary logic in digital domain to the equivalent quantum version. So to implement the quantum version, what we have to do is we cannot just um, um, remove the input state in the output, because then that means that for the typical for the quantum logic, we need to implement the unitary gate, which is reversible. But if we lose the original information, then we cannot recover the original information. So yeah, that's why we need some kind of copy of the input. But then we also need some kind of qubit, which will hold the calculation result. So this is kind of converting the digital logic to the kind of recipe to convert the digital logic to the quantum logic. And then once we can design this kind of circuit, then we can find out we can imagine building a unitary gate corresponding to this function. And then in this case, the quantum state will look like this one. So the input state will be expressed as the tensor product between the input qubit and some auxiliary qubit, which or yeah, sometimes this is called as auxiliary qubit or ancillary qubit. And then this additional qubit will serve as the container for the calculation result, and then the output state will be similar to this one, and then that means that the output will be again the tensor product between these two value, and then we know that the first one will still contain the original input, and then the output will just appear like this one. Then the one thing we can think about is the following. So if this is the typical digital logic, then what we will do is just try 0 for x, and then 1 for x, and then so at least to figure out f of 0 or f of 1, then we have to repeat twice for each of the x possibility. However, for the quantum circuit, we can actually consider using the superposition. So instead of trying the only 0 or 1, we can try the superposition of 0 and 1, and then assume that we provided 0 for the y qubit input. Then the the um, current input, the process can be expressed in this way, meaning that input state, the input state for the first qubit or input qubit is the superposition of 0 and 1, and then we assume that the y input will be 0. So this is the tensor product, and then the unitary operator will be applied to the entire quantum state, but we know that this is the linear operator. So, and then this can be expanded as the summation of these two terms. So the unitary operator will be applied to each of the term, and then we know that this result of this one means that the x will be 0, like this one, and then the second qubit will be 0 XOR f of 0. But we know that 0 XOR with the 0 means that it will be just the other one. So it will be f of 0. Similarly, if we apply the u sub f to the 1, 0 state, 1, 0 input, then the resulting state will be just expressed this one, and that's according to the same logic. Having 0 for the XOR gate means that we can just ignore the entire thing. Meaning that if this is 0, then we can just ignore the entire part. And then then let's interpret the resulting state. Well, first of all, it looks like we actually obtained multiple results in the in a single process, and then for example, the final output state contains the information about f of 0 and f of 1 simultaneously. So maybe you might think that this is excellent, because instead of repeating twice, it just gave us both output simultaneously. But is that really good? Actually not, because if you remember that, let's assume that you want to obtain the f of 0 and f of 1 value, both of the value, you need both of the value. Then how can you measure those value? Well, according to third postulate, even if the quantum state is the superposition of the many vectors, when we measure, we can only measure one of them. So let's assume that we prepare this superposition state. If we measure, we can either measure this state or the second state. We cannot measure both of them simultaneously. And moreover, once it is measured, the quantum state will collapse to one of them, which means I cannot just process once and then measure both of them one by one. What we have to do is re-prepare the entire state over and over. And if you just try to find out these two values, both of them eventually, then in the worst case, you might have to run the calculation more than twice, because sometimes you might just end up measuring this one more than once. So the first time you get this one, second time you get this one, and then maybe third time you will get this one. So it is very inefficient if you are just trying to get all this information by processing, by providing the superposition input. So then when do we get the uh, advantage of the quantum computing? That's when you don't need to measure all of these values, but yeah, before your final measurement, if you can do some additional processing, which will combine these result and then find some kind of pattern, and then you will see such kind of example in the later in in the next lecture. But yeah, so um, as I mentioned, just using the quantum computer is not using quantum computer for every application is not efficient. Yeah, only when your algorithm, quantum algorithm, somehow can take advantage of the quantum system, then only in that case you can get the speed up. And then yeah, so yeah, you it will become obvious as we go along. And then yeah, let me just give you a little bit more formalism for the quantum parallelism. Here, my example only assume that this function takes only one bit, but there will be many functions which will take multiple value, multiple bits. And then for that case, what about this situation? Let's assume that we have 2 qubit, and then each of the qubit started as a 0, and we apply the Hadamard gate for each of the qubit. Then the output will be this like this one. Then because these are two separate qubit, we can think about the tensor product between these two states. And what is the tensor product between these two? Then, yeah, because it is the multiplication of the two sums, and then in that case, I have to consider distributive law again. Then it will be 0, 0, 0, 1, 1, 0, and 1, 1. And these are the final state or expansion of the that such kind of product. And what does this shows? It shows that the input state can be expressed as the some superposition of all the possibility. Then what happens if I increase the number of these qubits? Well, if we have n of the qubit, that means that we will have the summation from 0, 0, 0, 0, 0 to 1, 1, 1, 1 for the entire n qubit, which means that we would create the superposition of n to the n, 2 to the n state, and that's actually quite a lot. Yeah, even if we have only tens of the qubit, then this value is extremely large. So that's the actually quantum advantage. And then and this is sometimes called as the quantum parallelism. But as I mentioned, if your algorithm is not clever enough, then you cannot really take advantage of those quantum parallelism. So that's the topic we are going to cover in the later chapters, later lectures. So I will stop here for today.